Yeah, in the first chapter of Jatili, he tried to convince some wave packet concept and uncertainty principle. Yeah, and again, let me take the similar concept. Before getting into that one, we shall solve that example problem. Okay. Example number 2.6, because after solving that one, I can give some idea about uncertainty principle and what exactly that uncertainty principle you will understand here. Again, you should give some mathematical related interpretation. You should not give just a physical interpretation. You keep by keeping that mathematics in mind, you should give the interpretation that is the correct one actually. Okay. Otherwise, usually uncertainty principle is applied or interpreted in a very wrong way in many cases. Yeah. Again, what we have done is for free particle. Yeah, any problem? Okay. For free particle, yeah, your stationary states or definite momentum state, those are like this. Am I right? A e power I kx minus h bar k square by 2m into t, and these are not normalizable. That's why we stated that there is no stationary state of free particle, or there is no definite energy state. That is definite momentum state also. Okay, and then we got that linear combination of this one. So since it is continuous with respect to k, continuous with respect to energy, so continuous energy again. So there is no boundary condition and all, isn't it? After solving differential equation, we haven't got any boundary condition for free particle. Remember, particle in the 1D box was also free, but only within some region. You got one mathematical boundary condition after solving, isn't it? Wave function should go 0 at x equal to 0, at x equal to a, isn't it? That boundary condition did, I mean, very difference, remember. That leads to quantization of energy. That leads to what you call our wave function, which depends on some integer, sine n phi x by a, isn't it? Everything is because of that boundary condition. For free particle, there is no boundary condition. That's why there is no restriction for k, there is no restriction for energy. Is that okay? Energy is equal to h bar square k square by 2m, and momentum we write it as h bar into k, like that, isn't it? There is no restriction on any of those. Now, but linear combinations of them, those are normalizable solutions, isn't it? And we have written 1 by root 2 phi integral minus infinity to plus infinity. We have written phi of k here, which plays the role of coefficient of linear combination, just like Cn into psi n, isn't it? Into e power I kx minus h bar k square by 2m into t, isn't it? dk, because it's a linear combination with respect to different k, different energy actually. Just like summation over Cn into psi n, isn't it? That's what you have written, that those psi n are states of different energy, isn't it? Coefficient depend on n, here coefficient depend on k. So their states are defined by n, quantum number, in case of 1D box. I'm comparing it with a 1D box, is that okay? Here states are defined by k. Can I say like this? Yeah. So that's why it should be integration with respect to dk, their summation with respect to n. Now this is normalizable solution, and we found that psi of x comma 0, that's equal to 1 by root 2 phi integral minus infinity to plus infinity phi of k e power I kx into dk. And now we got that this is nothing but Fourier transform, and inverse transform will give this coefficient. Phi of k is equal to 1 by root 2 phi integral minus infinity to plus infinity psi of x comma 0 into e power minus I kx into dx. Be careful. If you integrate with respect to dx, this whole thing will be function of k. We call this as momentum space wave function. We shall talk about that one later. Okay, I think not in this chapter, third chapter again. Momentum space wave function, how to use that one and all. Okay. Yeah, these were the whole story, whatever we have done in the morning. Now let me do example number 2.6. Okay, example number 2.6. Now look at here, observe this example very carefully. Yeah, wait a second, I got some question. Yeah, definite momentum state is also not possible. Look at here, definite momentum state means it is a solution of, look at here, if p cap psi is equal to some constant into psi, okay. If it is a eigenstate, if psi is the eigenstate of moment, now look at here, I have written eigenvalue equation with p cap as an eigenvalue operator. Now if you solve this differential equation, minus I h bar dou psi by dou x is equal to c into psi, is that okay? If you separate the variable, or let me call it as k or p, scalar p. So can you again, usually later we write like this, okay? Can you just have the difference? This is operator, this is scalar. P cap operating on psi, scalar p. Scalar p means it's not an operator, it's a constant into psi, eigenvalue equation, okay? Now if you solve this one, what will happen is d psi by psi is equal to I p by h bar into dx, just check it out. When you integrate, you will get ln of psi is equal to some I p by h bar into x plus some c, psi is equal to some a e power I p by h bar into x. This is nothing but a e power I k x. P by h bar I have written p is equal to h bar into k. So this is momentum state also, definite momentum state also, okay. Now look at here, I proved without Schrodinger equation. I have taken momentum eigenvalue equation and I proved you got the same state. And in the morning I did in the reverse way. I got this state by solving Schrodinger equation and I observed that is also definite momentum state, okay. Yeah. And again, definite momentum state, this is not normalizable, okay. It's not normalizable. Yeah, again you can say like, yeah, that's a good comment, okay. Definite momentum state. Yeah, wait a second, I'll give some more insight. Actually now again I'm trying to avoid that one because those physical insight, those are time consuming, okay. That's a very good story. Again, if you take psi is equal to a e power I k x, in this state actually you can't find sigma. Why? To find sigma you should find expectation values, isn't it? How do you find expectation value? Only after normalization, okay. But still, again, our logic says that there is no uncertainty in the measurement of p. You know that what is the momentum of this state? What is the momentum? P is equal to h bar into k. You know that one definitely. In that logic, let me say sigma p is equal to 0. Then sigma x tends to infinity according to our uncertainty principle. If sigma x tends to infinity, what do you mean by that one? If you do x measurement, you are getting the value, I mean, again, you are getting very wide range of values, isn't it? Dispersion in the curve. So can I say like this? Again, your mod psi square will be like this, or you can see this one. If you take mod psi square, that will be constant. That's nothing but mod a square. You can see that one, isn't it? Definitely, it is not, again, its position uncertainty is very high or infinity. And again, this mod psi square also talks about the same thing actually. Yeah, let me talk about one. That's a good idea, okay. In 1D box, it is different because boundary condition changes everything. Boundary condition changes everything. Wave function is 0 outside some region, isn't it? That changes everything. Normalizable solutions, you have some finite uncertainty, you have some finite sigma x and sigma px value that we found, isn't it, for nth stationary state as well as for linear combination state, isn't it? Again, that tells us that again, in case of bound state, that was bound state problem, we can have definite energy state. And in that state, again, look at here, again, that is a possible state, am I right? Physically accepted one. 1D box states are physically accepted that one, isn't it? But they are not states of definite energy, they are not states of definite position or momentum. Observe that one. Because each of them have got some sigma p and sigma x both are non-zero and product is greater than h bar by 2. We have shown that one in the problem. So that means it tells us that you can never have the state with a definite momentum or position. Again, the logic says that, again, after seeing those problems, you found that you got again only states with a definite energy, not state with definite momentum or position. Again, here comes the problem. Look at here. You can't have definite state of momentum. You can't have definite state of position also. Let me argue later. Is that okay? That's why you can't have definite momentum or position state. Rather than that, in Griffiths, in somewhere he defined that position and momentum. Again, we cannot have any state where position or momentum are well defined. You cannot have any state. Again, you can't prepare a system with a state where position or momentum, which are very well defined. Again, either this one or this one. You can't prepare these states. Those kind of states are not normalizable. Either this one or this one. You can check it out. Okay, we shall do that one again. Yeah, again, you can say, again, in case of definite energy state, I think I have interpreted, am I right? There is no energy uncertainty. There is no uncertainty in energy. There is no standard deviation in energy in case of eigenstate, energy eigenstate, 1D box energy eigenstate, isn't it? Sigma E equal to 0. In that case, again, you can use your energy time uncertainty to say that, again, it will stay there for a long time. Uncertainty in time, that is infinity. I'm talking about delta E, delta T greater or equal to h bar by 2. If delta E equal to 0, delta T will tend to infinity. It will take infinite time to have any changes. That means it will not change. Is that okay? Again, that's another story. I'm not getting that. Energy is everywhere. Energy is not that energy is everywhere. It is energy is continuous. Okay. You can't, again, it's not, energy is a constant. It's not a function of x or y or something. Okay. Here particle, again, here our potential doesn't have any minimum. Potential equal to 0. Potential doesn't have any minimum. If potential have got minima, you may have bound state actually. Bound state, I mean discrete energy state and all. It is not that case. So now let me move on to this example number 2.6 where I can give much more ideas about uncertainty principle. Now again, free particle, okay, whatever we are talking about, that is free particle, again, whose initial wave function psi of x comma 0, it is given like this. Psi of x comma 0, that's equal to, look at here, a, when x is between minus a to plus a. I think in the morning we have solved one Fourier analysis question, Fourier transform question, where it was 1 when x is mod x is less than, or x is between minus 1 to plus 1, isn't it? Similar problem. 0 when mod x is greater than a. Can I write like this? This is mod x less than a. X between minus a to plus a means mod of x is less than a, mod of x is greater than a. That means x is beyond those region. Or he writes otherwise. That's also okay. Okay. Now you should first normalize. Is that okay? You should first normalize. He said this is the state of free particle. Then it should be this kind of state. This cannot be of this kind of state because that's not normalizable. Okay. It should be this kind of state and we need to pi of k and all. Okay. Now look at here. We shall first normalize that one. When you normalize, what would you get? Mod psi x comma 0 the whole square integral minus infinity to plus infinity should be equal to 1. That will be mod a square integral minus a to plus a dx is equal to 1. I think that will be 2a. A is equal to 1 by root 2a. Am I right? Just check it. We had this kind of situation earlier. Whatever. If you put 1 by root 2a, that is normalized wave function, initial state. Okay. Again, any other normalization, the normalization procedure, again, I think he's talking about some box normalization. I think we should have some physical input to do all of those. Okay. Here there is no condition. Okay. There is no boundary condition at all to normalize, or I mean to give any what you call restriction and all. No restriction for k. So that's why it became non-normalizable. We shall talk about that one. Just see this whole story. Yeah. Now the next idea is, it is normalized, then I should find phi of k. Now look at here. Earlier we found again after finding psi n, we got psi of x comma 0. Then we have written this one as in terms of Cn into psi n. Am I right? You know this what you call expansion means you should know the Cn, or go to Fourier series. You know Fourier series means if you know a0, an and bn, that means you know Fourier series. Like that, this is also expansion. If you know phi of k, that means you know what is that expansion or what is that integral. Isn't it? This plays the role of this coefficient. Okay. Next idea is to find that phi of k. What is that phi of k? Phi of k is equal to 1 by root 2 phi integral minus infinity to plus infinity. So psi of x comma 0, again let me write psi of x comma 0 into e power minus I kx into dx. Can I write like this? Now again, this is 0 outside, it will reduce to 1 by root 2 phi. This is exactly the similar problem that we have done in the morning. 1 by root of 2a, but it is running from minus a to plus a, isn't it? Minus a to plus a into e power minus I kx into dx, 1 by 2 root a into pi, isn't it? And e power minus I kx divided by minus I into k with respect to dx, be careful, okay, minus a to plus a. Now 1 by 2 root of a into pi. Okay, let me take 2i inside, minus sign outside, okay, and k outside, 1 by k outside. What will happen here? 2i upper limit e power minus ika minus e power plus ika. Am I right? Again, if I do that one, that again, if I take negative sign and if I write, so shall I write again? Do these steps again yourself, okay? My phi of k would be 2 was taken inside, okay? 2 was taken inside. 1 by root a pi, okay? This is sine ka. Negative sign taken inside, this is sine ka. Sine ka. Sine ka divided by k. That's correct. Now what I do is, e power theta e power minus I theta divided by 2i. Sine ka formula, okay? I take a negative sign inside, 2 also inside. So now let me multiply and divide by a here, so that this will be equal to root of a by pi sine ka divided by ka, because I prefer writing in that way. Now you can plot this one, okay? You can plot this one. What is the range of k? K range is between minus infinity to plus infinity, remember. You can plot that one. That's a even function. As k tends to 0, it's a function of k. Okay, we call that in this momentum space wave function, that we shall see later. Now you can write psi of x comma t. Remember, right? Psi of x comma 0, which was equal to 1 by root 2 phi integral minus infinity to plus infinity phi of k e power I kx into dk. Am I right? You can write psi of x comma t, that's equal to 1 by root 2 phi. What was phi of k? Root of a by pi integral minus infinity to plus infinity. So sine of ka divided by ka into e power I kx minus h bar k square by 2m into t dk. Again, we are not going to solve that one again. I think if you solve, that's quite lengthy because you have time term also. You should take out time term outside again, but it's with respect to dk, be careful. That's quite difficult, okay, to solve completely. Anyway, yeah, he said unfortunately this integral cannot be solved in terms of elementary functions actually. quite difficult. Now, but we can do some interpretation, okay? We can do some interpretation. I have psi of x comma 0. Now, next part is pi of k. That was a root of a by phi sine ka whole divided by ka, isn't it? Sine ka whole divided by ka. Can we just plot this one? If you plot this one, this will be somewhere like this. Am I right? Minus a plus a. What is the height? Height is 1 by root 2a. This is your psi. Now, if you plot, or I better to plot mod psi square rather than psi, because yeah, whatever. Let me plot psi only. So similarly, if I plot pi of k, if I plot pi of k, it is this kind of curve actually. Can you see that one? Actually, I should practice little more on writing the board actually, isn't it? You can plot that one, okay? Just equal to, what is this one? The root of a by pi. Again, pi of k as a function of k. Pi of k as a function of k. Root of a by phi sine of ka divided by ka. As k tends to 0, sine theta by theta, that tends to 1, isn't it? So that this height is a by root of a by phi, okay? Height is root of a by phi. Now what I do is, again, I should have one more interpretation here. What is the use of that pi of k? Do you remember in case of this one, psi is equal to summation over Cn into psi n, am I right? Mod Cn square talked about probability of getting En, isn't it? Equivalently, in this integral of pi of k into, what is this, e power, pi of k into e power I k x minus h bar k square by 2m into t dk, these two are equivalent, am I right? We said like this, this is integral, this is summation, integral with respect to dk. Pi k is a coefficient, it should decide, mod square, it should decide, again, since it will have some, what you call, I told earlier, it will have some dimension actually. So mod square will talk about probability density, or mod, again, this is a continuous function of k, am I right? This was discrete, Cn was discrete. So that's why mod pi of k the whole square into dk, that is probability of finding the particle with the momentum k2 k plus dk. Sometimes loosely speaking I call k as a momentum, not k is not a momentum, h bar multiplied with k is a momentum actually, okay? Sometimes, because those are related by one universal constant, sometimes we say k as a momentum, because k will decide momentum actually. Is that okay? Again, why amplitude is decreasing? That's what you call. That's because of this function. Okay, try to analyze this function sine x by x. Okay, or you can think of 1 by k into sine k. Sine k is a pure sine curve. Am I right? But you divide by 1 by k so that again its amplitude will decrease like this. This envelope of this peak, again, that is because of 1 by k factor. Just try to analyze that function, how to plot and all. Okay, again, I just plotted it as it is. Try to analyze how to plot that function. That will not go 0 as k tends to 0. In that limit, this part will tend to 1. That's equal to root of a by phi. Okay. So this envelope is a 1 by k curve as a function of k. That's why the amplitude is decreasing actually. Okay. And remember that that again, that does matter, okay? That does matter. Try to plot again sin x by x, okay? Try to plot this one, sin x by x. Sin 10x by 10x. Root of 1, here root of 10. Because here you have a, isn't it? Which is root of a. Try to plot this. Root of 100 sin 100x divided by 100x. Try to plot and compare. What is the role of a in that curve? You should get what is the role of a, because you can change a here, you can interpret something here. Let me just so tell you some logic here. What is the role of a and all? But try to plot this one. Are you getting my point? Why I put this root of this value? Because root a comes. I don't worry about 1 by root 5. 1 by root 5 is common for all. I want to check out what is the role of a in that curve. So try to plot this and compare. Okay. Now this pi of k the whole square into dk, that will talk about probability of finding the particle with momentum p to p plus dp, or you can say k again with k value running from k to k plus dk. So loosely speaking, I call momentum ranging from k to k plus dk. But h cross k is what you call your momentum. Again, now can you grab the link here? That was the same story we had here. Here the coefficient, this had no, what you call, this was discrete, that's why just mod square got a similarity. Just find the similarity. Is that okay? Find the similarity. Coefficient mod square will decide probability, I better to say like that. Isn't it? Again, but coefficient will have some dimension. You should take mod square as well as you should multiply by dk, because it was continuous probability distribution situation. You don't have discrete probability. Now what I do here is, if there is more spread in pi of k, is that okay? If there is more spread in pi of k, uncertainty in the measurement of k will be high. If there is more spread in psi, then uncertainty in the measurement of position is very high, isn't it? Again, that is the logic, because again, after doing this interpretation, after grabbing this probabilistic interpretation, we can say that again, if pi of k, that's again mod square, if the distribution have got very wide spread, then definitely again, if you do the momentum measurement, is that okay? Again, you will get very range of value if it is widespread, isn't it? Now let me go to that situation actually. It's Schrodinger's talk. They are saying that whatever which is barking, that is Schrodinger's talk. Have I done any mistake on the board that Schrodinger dog is barking? You should not be like that. It should not be like that. And Schrodinger cat will bite, I think, if you do any mistake. Schrodinger dog will bark, isn't it? What is that one? Root of a by pi sine ka divided by ka. Can you remember these two actually? After writing couple of times, now I just remember this one. Now what I do is, I'll give you two situations, okay? Now what I do is, I'll make this a very small. When a is very small, 1 by root 2a, a is in the denominator, that will be very high, okay? When I do like this, what will happen here is, in that curve, in the curve of psi, look at here, when a is very small, you will have very high, this height is what you call large actually, minus a plus a. Can I write like this? Can I draw like this? What I do, I make a is very small, psi of x comma 0 or psi. Let me just simply write psi. Is that okay? As a function of x. This height is 1 by root of 2a. When a is very small, definitely this is very high, isn't it? Now look at here. If you take mod square, area under the curve should be equal to 1, isn't it? Now, if you are shrinking this one, obviously the height should go larger, so that area under the curve should be equal to 1, isn't it? Again, somehow it should compensate. Actually, I should have drawn this one little, lower. Again, area under the curve, not this one, mod square, area under the curve should be equal to 1. That's why if you want to shrink this one, obviously it will go very high, so that area under the curve should be again equal to some value, isn't it? Yeah. Wait a second. Let me talk about that. Now look at here. Your wave function is 0 outside minus a to plus a. Now this region is very small. Now in that situation, you can say particle is somewhere between minus a to plus a. Think about mod psi square. That's probability density of measurement of position. Particle is somewhere between minus a to plus a. And that region is very small. This is a very well defined position state. Can I say like this? Your position is very well defined. You can say particle is somewhere within this very short region, isn't it? Particle doesn't exist outside that short region. It has very well defined position. Is that okay? Now look at it. If I prepare this kind of state, look at here. If you plot for a is very small, you can just plot your phi of k, okay, your phi of k, and you should have some experience here, okay, while plotting this one. That will be this kind of curve actually. What is that one? Root of a by pi sine ka divided by ka. When a is very small, sine theta by theta, that is nearly equal to 1, am I right? Yeah, I better to plot like this. Now which has very, spread is very wide, look at it. When a is very small. When a is very small, k should be large to touch 0. Wait a second. I'm thinking on this one. I think that is correct, okay? That is correct. Just have experience in plotting whatever I gave. I gave some curves. Just try to plot that one. You will experience this one. Is that okay? Now look at here. Now if you try to interpret mod phi of k the whole square, that will talk about probability of measurement of momentum or k. Both are same. H bar k is momentum, okay? Now if you do momentum measurement, look at here. You got very wide range of values and sigma p is high. Is that okay? Here sigma x is low. Why? Again, spread in the measurement, outcome of the measurement, that is very low here. If you try to prepare a state with very well defined position, automatically momentum will be ill defined. I think I argued that one, am I right? Using that diffraction experiment, isn't it? It will be automatically high. So that product is greater or equal to h bar. Product is greater or equal to h bar by 2. Not only product, I am talking about, just forget about product for a time's sake. You are trying to define very well defined position and momentum is, without no control. It is ill defined. Isn't it? That's what happened, I think, in case of that experiment, diffraction experiment we have discussed, isn't it? When we try to make that slit width very small, your particles are widely scattered, which had very wide range of y component of momentum, am I right? That's what we observed. So again, if you try to define very well defined momentum state or ill defined position state, let me take like this, okay? Now let me take A is very large. Then what will happen is psi 1 by root 2a. When a is very large, this is very small. But area under the curve should be same as area under the curve of this one after normalization, isn't it? So again, so that somewhere here I have A here minus A here, very large. Now in this situation, sigma x is very high, isn't it? Because if you do position measurement, you got very widespread result. You should do the measurement on identically prepared system, okay? I hope you kept that one in your mind. But if A is very large, again, try to plot whatever the curve I have given. What will happen is this will be root of A by phi. When A is very large, this height is also, when A is small, look at here, this root of A by phi, this was root of A by phi, am I right? When A is small, this is also short actually. That's also short. Again, it will be like this. Root of A by phi sine Ka divided by Ka, that's your pi of K. It will be like this. Let me start with this one. If you try to prepare a state, with very well-defined momentum, now look at it, you know that again h bar k is momentum, okay, not k. You can multiply with h bar. Now, what is the range of momentum? It's very small range, am I right? Again, measurement outcome, think about measurement outcome. Again, your sigma p is very low here. Automatically you should pay the price here, that is sigma x is very high. Is that okay? So uncertainty is an inbuilt phenomenon, you don't have any control over it. If you try to prepare a state with very well-defined position, momentum will be ill-defined. If you try to prepare a state with very well-defined momentum, position will be ill-defined, okay? Yeah.